Alright, let's take a look at lesson number 13. We're in Unit 4, still thinking about exponential equations and logarithms. And we're going to see, as we have seen before, that we're going to play with a well-known base, and in this case it's base e. Now, we learned in lesson 12 that e is an actual number. It is also a button on our calculator. So remember that e is very much like pi. It's a number that's so important that it has its own name and its own symbol that goes along with it. Pi, of course, we know has to deal with circumference of a circle, an area of a circle, and it's approximately 3.14159. E also has its own value, founded by a man named Euler, which sounds like it starts with an O, but actually starts with an E. And as you can see in our calculator, e by itself is 2.7182818281828. So it is this repeating decimal, but we like to abbreviate it just as 2.718 is often how we would shorthand that. Using e gets us a nice specific value, and we're going to see today why e is such an important useful tool and one of the most famous formulas that we have in Algebra 2. If you need e on your calculator, I'm going to show you right now. It's above the divide button, so you see how it's got an e right here above divide. Right above the caret button, the one that turns things into an exponent, is the pi button. So if you ever needed pi, you would just type second caret, and you see that a nice pi shows up on your calculator, 3.14159. And similarly, right above the divide symbol is the E button, so we need second and E on our calculator. That's where we're always going to find that button. So as we use that more and more, you know where it's located, and a quick refresher. Now we're looking at items with a base E. So we've talked about examples of base 10 that we use, and even some examples that don't have base 10, things like time, months, years, days, seconds, and binary, which uses a base 2. So here we're going to see base E, and we have its approximate value, and we're going to be using our calculator for a lot of this, because just like pi, we can get a lot more exact if we have the exact value in there. Move that cursor out of the way. Alright, find the E button on your calculator, as we already looked at it. So we can do all kinds of things with E, like multiply it by 2, or take it to the second power. So finding E on your calculator and raising it to the second power gets us something that's 2.7 times 2.7-ish. So it should be a nice value looking like that, E squared. It's very close to having 3 squared, so it's between 2 squared, which is 4, and 3 squared, which is 9. Closer to 9. We can also multiply e by 2. So there's lots of things we can use it for, just like any other normal number. And so when we're looking at evaluating expressions that use it, this is just a quick test to make sure that you're typing things in correctly and you're able to find the values that we are expecting to see. So this is asking you just to test that 10 times e raised to the 1.1 power should get us approximately 3.04166, and that is what we're looking at here. So we see a nice match happening. Just go through each of these and double check that your calculator is giving you the same value. And it might also depend on how you're typing it in. This is an example that you likely, depending on what model calculator you have and what software it's got with it, you might need to put that exponent in parentheses, that 1.1 times 7. You might need that in parentheses for our exponent so that you're getting the exact value that we're looking for. So double check and see that you're putting things in correctly in order to get the right values that we're looking for. Another thing to also remember, if it's a fraction, you probably also need that in parentheses. 9 divided by 23, close those parentheses. If yours is like mine and actually shows it like an exponent, you need to hit the right arrow button so that it goes back to full size before you put in the +7. Another thing to keep in mind, how tricky these calculators can be. Once you've played with your calculator and you're getting all the exact values that they're looking for here, we're ready to put it into action. So I'm going to turn the page. Let's look at 13.2. We see a same situation, different equations. And so the most important use of E is at this thing that's called continuously compounding. I'm actually even going to write that. I'm going to put it right up here. If something is continuously compounding, that means it's constantly growing at a consistent factor, right? So all of our exponentials that we've looked at, we're always drawing graphs that show exponential growth, something like this. And we may take snapshots and say, hey, we know the population here to start with, and then we know the population 10 years later, and what is that growth per year? But in reality, when people are studying nature or science, when you're looking at medicine or really all of this stuff, it's happening continuously all the time in these itty bitty little increments. So it's not just that the population grows at the beginning of the year or the end of the year. It's growing and changing every single day along the way. So continuously compounding gives us this idea that it's making these itty bitty little changes all along the way. So this colony of insects starts off with 9,000, and I see both equations have the same starting value to represent that 9,000 insects when it is first studied. And when we look at these two factors and their exponents, we see some interesting differences. This one tells us that it's keeping the full 100% every year, and it's adding 2% to its population. And it looks like not every year, every month. So it keeps its 100% and it adds 2% each month. And so we can find that nice equation, that formula we would use, so we can find it every single month. This one, though, uses base E. And you'll notice that it has the same starting value. This time the factor is just E. And then the exponent has the amount that it's growing by. Now notice here it was 100% plus 2% more. Here it's just the 2% that it's growing by. So here is where that growth factor is. And then the t as we had before. So two big changes in these equations that we have. Same starting. T is still in both exponents. But one of them has the factor in the normal box where we see the factor. And our other one, I shouldn't even write the word factor there because we don't even want to confuse it with the other growth factor. Our factor is E, and here is the rate that it's adding, that it's changing by. It asks us to use technology to find these, and so when I'm looking for multiple input values here with T, it makes the most sense for me to go to my y equals and type each of these equations in. So 9 times 1.02 raised to the x in my y1, and in my y2, 9 times e raised to the parenthesis 0.02 x up there. And now I'm going to use my table of values in order to calculate these. My table is set to start at I guess it's going to start at 0. I'm going to make it that way. The first value we need actually is when x is 6. And so I see our two values here. So my population P in thousands at 6 months, 10.135. And for my second equation, I've got 10.147. And we'll fill in this table for each of the months requested. Keep on trying to focus, and it seems like my camera won't focus very well on that. I notice they're starting off pretty similar. Let's go down to 24. Here is where we're starting to see a bigger separation. So after filling out this table with my two equations, I notice the populations of these two models start very similarly, but the bigger our time gets, the bigger the exponent in each case, the farther apart they go. So I'm going to say the larger the input that we give it, the more time we give it, the farther apart the two population values become. So they are. The longer we go, the farther apart they seem to be getting. And that has to do with how we have something that is continuously compounding. So the idea that in our first equation, it's, I don't want to say it's like rounding, but it is. Like banks have these calculations where they take certain calculations that they're running all the time, and they have to round the little partial pennies, and oftentimes they just round them down and they collect the difference. Here, that bank would be giving you those partial pennies all the way through. They'd be keeping a running total and giving you those partial pennies. So they're going to start getting farther and farther apart. In fact, if we look at the graphs of these two, especially over a certain window of time, I'm going to start with a zoom 6. And it's going to be not showing me what I'm looking for. But if I start at a time of 0 and I go up to 100, my Y scale is going to have to be up in the 66s, so I'm going to make that maximum 100. And when I go look at the graphs of these two, well, here's my first equation. And I'm expecting my second one to always be just a little bit higher, and it should get farther and farther apart as the two go along. Now those are almost identical. They're almost on top of each other. But if we really start to zoom in, we can see that that difference in the two is going to get farther and farther apart the longer it goes. Question 3 tells us we have a pair of equations representing populations in thousands of 4 insect colonies in the research lab. Each one of them has an initial population of 10,000, and they're all growing exponentially. It asks us to graph each pair of functions on the same coordinate plane. Now you can use Desmos, since you already have a Chromebook out and you're watching this video. So you could graph these on Desmos and see what they're looking like, but it gives us a window to look at. So I'm just going to use my calculator and graph each pair of functions on the same coordinate grid. And to see what we notice about the graph of the equation using E and the counterpart without E, make a couple observations. I'm going to do this just for colony 1. I already have some ideas from our first example that we've done of what I might be finding. Putting in my 2 equations. Sorry, that glare was pretty rough. So I put in my first colony 1 equation, my second colony 1 equation in the same coordinate grid, and it asks me to have my x's from 0 to 50 and my y's from 0 to 80. So I'm going to go to my window, my x's from 0 to 50, my y's from 0 to 80. This way we're all looking at the same kind of window of information. And here's my first graph. And black. And this one you can see a little bit better. My second graph in red, as it gets higher and higher, see how they start getting a little bit far apart. So I'm going to put a red dot on that one, so I remember that one's the one graphed in red. And it starts off right on top of it, and then it kind of starts to go a little bit separate like that. I'm going to hit pause, and I'm going to draw the same picture for each of my other colonies. Please do the same with me. Hit pause on this video, and let's see what happens as we go forward. Alright, so I hit pause, and I have all of mine now graphed into my equation. So I have my 2 equations for colony 2, my 2 equations for colony 3, and my 2 equations for colony 4. I'm going to graph them all at the same time and kind of show you that drawing of what they're looking like, although you're probably seeing the same thing. Although sometimes it's nice to see it in color like this. So here's these 2 that are coming in right now. And you can see that they are almost right on top of each other, but the second one at the end goes a little bit higher. Here come the next 2. Almost completely identical. And my last 2 for colony 4. They're like right on top of each other. You can see the color just coming right on top. So it seems like colony 1 is the farthest apart as we go along. Colony 2 gets a little bit far apart, and then colony 3 and 4 are almost identical, almost right on top of each other. So when I look at some things that I notice, they all start very similarly. Almost on top of each other. So each pair starts off almost on top of each other. And something that I started to notice is that the farther along we went in the colonies, the more they stayed on top of each other. So the thing that I noticed that changes between these, this one is looking like it's adding a 5% to it, so that's a rate of 5% that it's adding. This one's adding 3%. This one's adding 1%. I'm getting this right here from the rate that we have in both cases. And this one's adding just a 0.5%, 0.5%. So another thing that I noticed is the higher the percent change in population, in this case, the higher that percent change that we have, the farther apart the graphs as t gets larger. So the difference between the 5% colony here is more drastic than the difference between the 0.5% colony. The higher the percent change in population, the farther apart the graphs get as we get to higher numbers of t. So we can see that this could really be a big change in what we expect to see in populations or money or account values as we get higher and higher. The most famous use of E in exponential models is this equation right here. We use E in this kind of a situation. We have our output at a certain time, or input value, equals the value of the function at 0. We've been calling that our starting value. Times constant E, our continuous growth rate, in this case 4.5%, because we turned that 4.5, remember bumping it 2 decimal places, that 4.5%. When we put it in as a decimal, we bump that 2 places, 0.045. And our input. We'll often shorthand this as the PE to the RT. P is often used when we're talking about principal. That's our starting amount. In money, it's called a principal. How much are you investing in something? E is our constant. R is our rate of continuous growth. And just like this, it's the continuous growth rate. It will call it that. It'll tell us that it's continuously growing or compounding continuously. And then T is our time of how long we're letting it be there. So you might see this as a nice example to look at, but you might also see it shorthanded as PE to the RT. So down below we look at some situations, and it's just asking you to identify, hey, what is the starting value of the function? What is the continuous growth rate? How long are we letting it sit there? So by writing it like this, we can see some different values that are happening, and you see we're going to start picking some values out and seeing what we should be putting in there. So number 1 reads, at time 0, measured in hours, a scientist puts 50 bacteria into a gel on a dish. There's our starting value at 50. The bacteria are growing and the population is expected to show exponential growth. It gives us this function and it asks, what is that continuous growth rate per hour? Well, we see the E here, so that's our signal that we've got continuous growth rate. And that rate is happening here in our exponent. So if I see a growth per hour of 0.25, we can say that that is our continuous growth rate, 0.25, or we can write it as 25% per hour. In 1964, the population of the United States was growing at a rate of 1.4% annually. That year, the population was approximately 192 million. I'm guessing that's going to be our starting year right there, our starting amount. So we're starting with a population of 192 million. We have the E there. PE to the RT, we need this rate. And so if we have a 1.4% rate, we have to turn that into a decimal, bump it 2 places, 0 placeholder. So it's a 0.014 in our exponent. Number 3, in 1955, the world population was about 2.5 billion and growing. There's our starting amount. The model predicts the population in billions after T years, after 1955, uses this model. So we've got our starting amount of 2.25. We have our growth rate, 0.0168, or if we like to see that as a percentage, 1.68%. So we're just starting to practice about how to pull those numbers out of a word problem and put it into an equation, into a known formula, always using P times E to the RT, P-E-R-T, P-E to the RT. Probably hear me say that a lot in the next coming times. Last section here in lesson 13, graphing exponential functions with base E. We've already practiced some of this using graphing technology, so I think we're going to be A-okay. So it tells us we need to use technology to graph this. Let's go erase everything that's in there. Or if you're on Desmos, clear out what you've got, and we're going to enter in our new equation. 50 times E raised to the 0.25x and adjust the graphing window as needed to see what's going on. Alright, so the function f models the population in hours after it was initially measured. About how many bacteria were in the dish 10 hours after the scientist put the initial 50 bacteria in the dish. So we've got our starting amount, matches. This model is in T hours, and it's asking us for 10 hours, so I can just put 10 in place of T. So T equals 10, according to our equation. You can use a graph to see it, but as long as we've got this value here, we might as well use our table. And I know I need to go change my table settings to start at 0, change by 1. And we're looking when we've let 10 hours go by. And that looks like a nice population of some pretty quickly growing bacteria of 609.12. And then it asks us, about how many hours did it take for the number of bacteria in the dish to double? Alright, to double. Let's see, if I start at 50, doubling means that we're looking for a value, an output. Put that word here. We're looking for an output of 100, because we want to double that amount. So up here, we actually could have also just, instead of using the table, we also could have calculated plugging in 10 for T. We could have multiplied 0.25 by 10 and calculated that. Here, though, I'm looking for an output of 100. Now we can, again, use our table of values here and start getting smaller and smaller increments. Right now we know it's happening somewhere between 2 and 3 hours, but I want to refresh you on a way we can get a nice exact answer here. Go back to your y equals. If we want the output to be 100, let's put in our y1 and our y2. Let's have it equal the 100 that we're looking for. I'm just writing this down so I can show my work and so I remember how I found this stuff a little bit later. So I'm going to graph these two, and I'm going to look for the intersection point. Refresher on how to do that on your calculator. Right now my window is going to show me up to 60, but I want to see up to 100 and a little bit more, so I'm going to go to 110. That's going to give me the output, the Y value that I'm looking for. Let's go look at the graph. Whoa, it's just over here, so I don't even need an X anywhere near this big. There's my line at 100 that just graphed in here. So if you want to adjust your window so you can only see some values from 0 to 10, that's a little bit nicer of a graph to look at. My line for 100 should be coming in here any second. I'm looking for that intersection point. Don't trace and guess. Right above your trace menu is the calculate. So second trace button takes you to the calculate menu. And we're going to go down to the intersection. Move your cursor left and right until you're close. Mine looks like I need to go to the left. If you're ever having trouble finding your cursor where it is, use your X values, your X and Y coordinates. When you're close, hit enter 3 times. Enter, 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 until it tells you the intersection happens at 2.7725887 years. Remember, we're going to 3 decimal places in our classroom. So we would have 2.773 years. One last question, we're almost done. Graphing technology, we have a new equation. Hit pause on the video. Put in your best answer. Just want to check and see if you've got this down. one last step on this one. This one told us how long it was going to take, like how many years it takes to get there. But it says, in which year does the model predict it will reach 300 million? This is 31.8 years after 1964. So we just need to add one last idea. We have 1964, and we're going to add 31 point, I don't know, 0.8-ish years or 0.9-ish years. Really what we're looking for as an answer is that this is going to happen most of the way through 1995, but not quite 1996. So it's going to happen in 1995, most of the way through it. That's our lesson 13 summary. Our big idea is the PE to the RT formula. It's got it right there for you too, so you might want to highlight that idea. We're going to use this every time we have continuous growth rate, another key idea going on here. When we see continuous growth rate, we're going to use E as our multiplier factor, and we're going to take that continuous growth rate and use it as a decimal in our exponent. That's our big summary from lesson 13. Good luck on those practices. I know you've got this.